finding a problem because I have two junior undergrads who are
governors took on that responsibility. Of course, they don't have any staff either. They didn't know what this was about.
oh, so the approval is coming.
Yeah, it goes through the board of governors. This goes all the way up to political.
Oh my gosh.
So this is designed to do what it does. It's essentially cut dollars down.
I mean, I felt so bad. And this goes back quite a ways. It's about 20 years ago. I had a foreign student from Bulgaria. Her parents were both, I think, physics professors. She had a brother who was a physics doctoral student here. And she was really smart. Bulgarian was her first language, Russian was her second language, English was her third language. She was doing English crossword puzzles within 6 months after getting here. And I told her that I feel so bad that we're taking, these best graduate students. And she said, if I would stay in Bulgaria, there's nothing for me that I can do. And she had a brother who was a medical doctor. He said after the fall of the Soviet Union, he was selling sandwiches on the street because there was no work for him. And then he wound up dying young. So, yeah, I mean, I came away thinking, yes, it's a whole lot better to be in some place where you can actually do something than be in a place where you can't. Okay, it is 10 o'clock.
Yeah,
So
I guess we can get her started. All right, so my name is Chandler Pruett, and I am going to be talking about my thesis that I've been working on since May of last year. It's on tropical cyclone reconnaissance missions. Thankfully, I'm able to present it this week instead of last week when we had that 100-year flood. So let's go ahead and get started. First, here's an overview of our results for this study. So I cataloged the average frequencies of reconnaissance wind speed observations in specific intervals. So basically, I looked at certain wind speed intervals starting at 0 to 34 knots, then 34 to 50 knots, and increasing from there. But basically what I was trying to answer is what percentage of observations do they spend in each storm? So basically a proxy for how much time did they spend in each part of the storm when they're when they're observing the winds in the tropical cyclone. And what we found was that for Category 1 hurricanes and greater, the maximum frequency occurred in the 34 to 50 knot interval range. So that means for a Category 1 storm, the 34 knot to 50 knot wind speed interval range, that's where the most observations were taken compared to the rest of the intervals. And that's the case for Category 1 all the way up to Category 5 hurricanes. Then we also evaluated the chronological success rates of gale force potential intersections, GFPIs. And we'll talk about momentarily what those look like, what GFPIs are, but basically, if you have your hurricane that's flying through the eye of a storm, and then it's basically exiting the storm, and it wants to turn around and re-enter the storm, when it's doing that turnaround motion, does it successfully cross the 34 knot wind radius? If it does, that's a successful GFPI. If it turns around before reaching those 34 knot winds, or before reaching those winds below 34 knots, then that means it was not successful. So we found that the GFPIs in earlier parts of the mission are the most successful. We also analyzed the linear relationship between the number of successful GFPIs and the mission peak wind, the Vmax, velocity maximum. And we found a statistically significant inverse relationship, basically saying that as you survey stronger and stronger hurricanes, the number of successful GFPIs decreases. Now, the motivation for this study. So I'm a hurricane analyst for Moody's RMS H-Wind, which was first founded by Dr. Powell. And so my job is to analyze wind structure of tropical cyclones. But we have to use data, of course, to analyze that wind structure. And usually our two main sources of data are satellites and reconnaissance observations. Well, satellites are polar orbiting. So there's instances where the satellites won't be detecting winds for that cyclone because maybe they're on the other side of the globe. And for those instances, then all you're relying on is the reconnaissance missions to understand basically the structure of the cyclone. So let's say you have a mission where the plane enters the storm, so you have a successful GFPI when it enters the storm. And then whenever it's flying inside the storm, it stays within the 34 knot wind radius. So you never see where the 34 knot wind radius is. All of a sudden now you're thinking, how large is this 34 knot wind radius? It could be very large, and you just don't know what its bound is because the reconnaissance mission wasn't flying out far enough to reach that threshold. So moving on, there is no past research linking the flight patterns of low-level reconnaissance missions where they're flying really close to the ocean surface and hurricane structure forecast. There is research done on the G4, the Gulfstream 4 aircraft, which flies very high in the atmosphere and observes the upper atmospheric environment for tropical cyclones. There was research done on how that flight pattern impacts our structure forecast, but there's no research that has been done on the flight patterns for the low-level reconnaissance missions. So kind of wanted to try to fill in that gap. And also, of course, with understanding tropical cyclone structure, it's important because that impacts how we forecast the magnitude of hazards such as storm surge and rainfall. And also impacts how we understand the timing of those hazards, the geographical extent, and the duration of those hazards. And lastly, I mentioned the polar orbiting satellites. Well, the number of suitable satellites that we use is expected to decrease over the decade, exacerbating that data coverage problem. So our objectives were to address the data coverage problem by first understanding how much time the reconnaissance missions spend in each sector of the storm. So how many observations they spend in their, it's either the 34 knot wind range, what their percentage is for 34 knot to 50, and increasing from there. And so we documented the distributions of the observation frequencies in those wind speed ranges. And then we addressed the gale force wind retrieval methods by basically detailing those instances where the flight paths attempt to intercept the gale force wind threshold, and then evaluating the successful GF threshold intercepts chronologically and against the tropical cyclone strength. Now, before moving on, when we're talking about the surface winds, how are those detected? Well, they're detected using the step frequency microwave radiometer. It's a mouthful, so we're just going to call it the SFMR. That's on board both the NOAA P3 Orions and the Air Force's WC-130s, both of which fly very low to the atmosphere between 900 and 700 hectopascals. And during this during these missions, the SFMR is pointed towards the ocean surface and detects the microwave radiation emitted by the ocean surface. Keyword ocean, does not work over land. But what it does is it detects the microwave radiation emitted by the ocean surface through brightness temperatures. And those brightness temperatures change based off of the wind speed at the surface. Of course, stronger winds are going to create a rougher ocean surface, which is going to alter the brightness temperature. And thus the SFMR can detect that and adjust the wind speed estimation. Now that signal does get attenuated by high rainfall rates. So in instances where there's really heavy rains, you can alter that brightness temperature that the SFMR is detecting. And thus your measurement can be biased. But SAP et al. Reduced the rain contamination for rain rates less than 45 millimeters per hour. However, that still does not fix all the issues. There are still many instances where there are wind speed spikes, even though the rain rates are lower. And we'll get to that momentarily. Now, a description of our data set. So we use the high density observations recorded between 2018 and 2022. And this data is stored in text files on the NHC's website. Now, the text files contain 12 variables measured every 30 seconds and recorded in these 10-minute increments. So basically, per each text file, there are 20 observations or sets of observations. Now, the variables that are recorded in these sets of observations, the ones that we used were observation time, the location, so latitude and longitude, aircraft static air pressure, the peak 10-second SFMR wind speed, surface wind speed, and the rain rate. Now, moving on, the biggest hurdle for this project was removing outliers. The SFMR is not perfect, and there are a lot of cases where you have a high wind speed. And so what we wanted to do is try to remove these outlying wind speeds, such as Mission 10 into Hurricane Sally, as you can see on the left-hand side of this screen. So we sought automated process because we had so much data, and we looked at basically trying to use rain rate because the SFMR has that overestimation bias that I was mentioning with the high rain rates. But there are multiple cases of SFMR wind spikes associated with low rain rates, such as Mission 10, where you have low rain rates for those 3 observations that are above 80 knots that are clearly outliers. So a lot of these instances are likely due to land contamination, where the plane is flying close to the coast or over land, and thus the brightness temperature is tampered with. So, of course, our automated process cannot depend on rain rates alone. So we tried a different technique, one that was inspired by me and my colleagues at RMS, H-Wind. And basically, when we were looking at these spikes and the wind speeds, we found that there's usually spikes in the rain rate. So as the wind speed increases dramatically and then decreases dramatically, the rain rates also increase dramatically and then decrease dramatically. So we wanted to basically find the second derivative of that rain rate. We call that rain rate change. And we wanted to see if that would help us detect these outliers. Well, while it added information, the RRC did not capture all the outlier cases, again, such as Mission 10 and to Hurricane Sally. So we switched to a manual outlier identification process. Now, even with the manual outlier process, I still created a flagging algorithm that basically prompted the user to investigate and remove data points that are flagged. Now, the algorithm first went through and chronologically arranged observations into groups of 100 or more. So it would take your time series of observations that are usually over 1,000 observations, and it would divvy them up into groups of 100 or more based on chronological order. So keeping along that curve that I was showing you with the time series plot. And what it would do is then use the mean absolute deviation to represent spread. Now, it actually used I used a pseudo MAD, where instead of mean, I used the median, just because the mean is biased by very strong or very large outliers. So I use the median instead of the mean when calculating the MAD. Now, with the flagging algorithm, it basically created an interval of acceptable values where you would add the median plus the MAD pseudo times the scaling factor, and that would be your upper range. And then for your lower range, you'd have the median minus MAD times the scaling factor to create basically an interval range of acceptable values. If a observation fell outside that range, then it was flagged by the algorithm. Now, in this case, the scaling factor was 10 because I wanted to decrease the sensitivity of the algorithm. If you keep that at, let's say, k equals 1, then all of a sudden it will flag every small little deviation from the curve. Now, once flagged, the data were assessed both quantitatively and qualitatively. Quantitatively using the rain rate and rain rate change, and qualitatively using both the geospatial plotting to identify those land contamination cases, and time series plotting, where I basically referenced the Wilby profile to identify observations that deviate from that time series curve. Now, during this process, I still was able to remove outliers that maybe were not flagged by the algorithm. There were a few instances of that case, especially whenever you enter into the eye of the storm. If you have a major outlier right in the eye wall of the storm, well, your eye of the storm, the winds naturally will decrease dramatically. So you have a big spread in your data, but then that means you're not going to capture necessarily that outlier that is deviating from the curve. Now, here's a case of the outlier removal process. This is mission 38 into Hurricane Dorian. And you can see the wind speeds above 100 knots are clearly outliers. And there's also a few other cases of outliers as well. And basically that flagging algorithm identified those outliers, and then I went in and removed them. And so zooming into that 10 to 80 knot wind speed range on the right-hand side of the screen, you can see the observations now kind of follow that curve, and we no longer have as many big deviations from the curve. Now, why can I reference the Wilby profile when analyzing the time series plot? It's because, you know, the Wilby profile is a function of distance. It's not a function of time like the time series plot. But the primary reconnaissance flight path is the alpha pattern. So that means that they're flying radially into and out from the storm. And as such, basically, distance and time are synonymous. So I can still reference that Wilby profile and reference what we would expect to see whenever flagging outliers. Now, moving on to how we analyzed our data. So we have this outlier adjusted data set. And what we did was for each mission, we threw it into these 6 different categories, depending upon what the Vmax of that mission was. So let's say you had a tropical storm mission, or mission into a tropical storm, and the winds are 55 knots. That means you would take, or the Vmax is 55 knots. That means you would take that mission and throw it into the tropical storm category, and you'd take every observation within that mission and throw it into these interval ranges. So all the observations in between 0 and 34 knots would be thrown into interval 1. All those between 34 and 50 knots would be thrown into interval 2, and so on and so forth for interval 3. And we did this for every category. So if there was a mission that was a category 5, we would throw that mission into that category 5 bin. And then for each of the 8 intervals, we would throw the observations into those intervals based off if they fall in that interval range. Now, the next step of our data analysis procedure was to look at the gale force potential intersections and how, or I'll walk through basically an example of how this works and how we found the GFPIs. So first, I'm going to show you the 34 knot wind radius for the this mission into Hurricane Michael. And you can see this is kind of what the 34 knot wind radius looked like. And let's start with the beginning part of this time series. We have at 20 UTC on the 9th, the winds are below 34 knots. So the plane is flying in those weak winds. But then it crosses over that 34 knot wind threshold. It detects that 34 knot wind radius like we want it to. So that is an example of a GFPI. And in this case, it's a successful GFPI. Then you enter the storm and you cross through the eye at about 20-30 UTC on the 9th. So again, those winds spike dramatically, and then they start to fall off dramatically. Now, then we have this little range right here. Sorry, let me fast forward. Now we have this little range right here where the wind speeds kind of oscillate back and forth between being weaker than 34 knots and being stronger. That is the chord of this alpha triangle is what we're going to call it, where basically the winds are flying, the plane is flying no longer radially in or outward from the storm, but instead is flying to where the radius basically decreases as it's flying towards the center of the storm a little bit, and then flies again away from the storm in this chord. And then it will reach an intercardinal direction where it then turns around and flies back radially into the cyclone. Now, during this process, it exits the 34 knot wind radius down there at about 25 degrees north. And then it re-enters whenever it's flying on that chord. So then the winds increase slightly. Before then, at about 27.5 degrees north, the winds again decrease as the plane exits the 34 knot wind radius. So this whole series of intersections, I ended up counting as one successful GFPI. If I tried to count it as multiple successful GFPIs, I would not have been able to do this analysis because I was looking at over 200 missions. And so I basically noted that for this, your lowest successful intersection or lowest wind speed in this intersection range was at about 30 knots. There near 21 UTC. So this alpha triangle was successful. It did cross over the 34 knot wind radius. Then you enter the eye of the storm again at about 22 UTC. Then you exit the eye of the storm and you make another alpha triangle. And this alpha triangle again is also successful as the winds do decrease below 34 knots and bottom out a little bit less than 20 knots actually. Now, as it re-enters the storm, it re-enters that 34 knot wind radius and approaches the storm again at 2330 UTC. It crosses through the eye. And then as the plane is completely exiting the storm, it crosses through the 34 knot wind radius one more time at about 0Z on the 10th. Again, making another successful intersection. So in this case, there are 4 successful GFPIs. That's not the case for every mission. And let's look at an example of that right here with mission 23 into Hurricane Dorian. In this case, you have 5 GFPIs, one at the very beginning, and then one after every peak, every eye intercept. And in this case, you only have one successful GFPI, and that's the very beginning, where the entrance into the storm, they do start off below 34 knots, and they enter the storm and cross over that 34 knot wind radius. Now, with our data analysis, this was performed for missions with a clear alpha pattern curve, these curves that I've been showing you guys for the last few minutes. So this did exclude weak cyclones where the alpha pattern curve is not obvious. You don't know what is an eye intercept and what is just a patch of very weak winds, because with tropical cyclones especially, they're very disorganized. You can have a lot of patches of super weak winds where it's not necessarily associated with the center of circulation. And you can have a center of circulation where the winds do not decrease at all. Instead, you just have winds that are around 34 knots, even in the eye of that system. So we ignored a lot of those cases that did not follow this pattern. But in total, we had over 261 missions in our GFPI dataset. Now, our data analysis step was rerun after removing observations made at pressure levels less than 650 hectopascals. We'll get to why here momentarily, but we recalculated the wind speed frequencies, and we also adjusted the GFPI dataset, reducing that size down to 211 missions. This adjustment also included the process of taking out landfalling missions because the reconnaissance could not complete the alpha pattern curves. Basically, you'd have an example where the plane flies into the storm, and then maybe makes one alpha triangle where you have a clear alpha triangle pattern, and then it would re-enter the storm. And then on the other side is a huge landmass, let's say the continental US, and they can't fly over the land. So instead they stay within the eye of the storm and just do a lot of zigzags and stay within the eye wall. And that's no longer their typical modus operandi. So With that in mind, we went ahead and just took out those landfalling missions just to see how the adjustment changed our relationship. And we'll get to that here at the end of the presentation. Now, the intent of reconnaissance is to fly at pressure levels of 700 hectopascals or greater, so between 700 and 900 usually. Unless there are 2 or more missions ongoing, then they have to give each other about a couple thousand feet in altitude difference. So with that in mind, there are fewer SFMR observations that were taken at pressure levels less than 700 hectopascals. So we cannot necessarily concretely confirm its reliability. The SFMR machine theoretically should work at those pressure levels greater than 700 or less than 700 hectopascals, but we just don't have as many observations to confirm that it theoretically should work there. And instead, we decided to ignore that and when we reran the analysis. Now let's get to the results. So we have these frequencies, and the way you can read these frequencies are that they're basically the average for all 6 categories. And so let's say you have a typical tropical storm or a mission into a typical tropical storm. About 71% of your observations will probably be in that 0 to 34 knot wind radius or wind threshold interval. Then between 34 and 50, that interval, you'll observe about 27% of your observations in that interval range. And then about less than 2% of your observations will be taken between 50 and 64 knots, which is something you would expect, that steep drop off, because you have many instances where you have a tropical storm with a velocity maximum at, let's say, 40 knots. So in those cases, you're not going to have any observations taken in that 50 to 64 knot range. Therefore, that tanks your average and makes that average less than 2%. Now, as you file through the remaining 5 categories 1 through 5, you see that the maximum frequency in each of those categories occurs at the 34 to 50 knot interval. What that indicates is the hurricane reconnaissance missions, the majority of their flight, they're observing winds between 34 and 50 knots, or at least compared to the other intervals. One other thing to know, of course, as you're increasing those wind interval ranges, your maximum frequency in those wind intervals increases in category. That's basically just to say that as you get into stronger wind intervals, where of course you only have, let's say we go to the 96 to 113 wind interval, your only options are missions into category 3, 4, or 5 storms. So your maximum frequency will be one of those 3 intervals, or one of those 3 categories, excuse me. In this case, it's category 4, which has a maximum frequency of 3.8% compared to 1.7 in category 3 and 3.56 in category 4 or category 5.
What's the yellow?
The yellow is just basically showing the maximum value in this column.
Okay.
The blue is showing the maximum value in the rows, and the yellow is showing the maximum value in the column. The more important takeaway is the maximum value in the rows, but I thought I would highlight the trend with your interval columns. Now, moving on, we have here a box plot that basically shows the distribution around these average frequencies. Of course, we were talking about how the average frequency for tropical storm missions with the 0 to 34 knot wind interval is somewhere around 70%. And you can see that here in this box plot. And you can see how basically you can have a mission where the frequency in between 0 and 34 knots is lower than 10%, or you can have a mission where the frequency of observations in between 0 and 34 knots is as high as 99%. So a wild variance in your frequencies in this 0 to 34 knot winds. And it's actually the same for your 34 to 50. You'd expect that because your tropical storms are not steady state. You can have a tropical storm where it's a rapidly decaying system, so your winds are really large. Your wind field is very large. They might not be strong, of course, but the wind field itself might be very large. Or you can have a case where you have a storm that's just starting to develop, and so its wind field is super small. So that explains why you have a very wide variance in the tropical storm category. So yeah, again, 34 to 50, that interval range, you can have a mission where nearly 0%, not actually 0%, but nearly 0% of the observations are taken between 34 and 50 knots. Or you can have as high as almost 90% of the observations are taken between that interval range. And then once you move on to the 50 to 64 knot range, you see a dramatic shrinkage in that spread. And that's something you would expect because you have multiple instances where you have 0% for the frequency of a mission, because you, again, have a mission maybe into a tropical storm that's super weak at 40 knots. That means that you're going to have 0 observations taken between 50 and 64 knots. Now, moving on to category 1, again, this widespread in the frequencies persists. You start to see a small shrinkage of that in the 0 to 34 knot wind speed range. You start to see the spread start to shrink a little bit, but again, it's quite large. And only once you start moving on to the 64 to the 83 knot interval range is when you start to see that spread really start to constrain around the mean. Moving on to category 2, you really do start to see the spread decrease with category 2, as you would expect with category 2 storms, hurricanes being a little more steady state. So they start to approach a little more of a steady state system, excuse me. So in this instance, you have, let's say, missions that could range anywhere from 0% of observations taken between 0 and 34 knots to as high as almost 50% taken between 0 and 34 knots. And that spread does, again, decrease as you get into stronger wind field or wind intervals. Category 3, again, that spread decreases again. But then once you get into category 4, the spread increases at the 0 to 34 knot wind interval. Not exactly sure why that's the case. It's just something that I found interesting because, again, you saw the trend, the spread starts decreasing as you get into more steady state storms. But here with category 4 mission, that spread is quite large. Maybe that's the case because we have a few instances where the missions are just higher in frequency, and therefore, since we have fewer observations or fewer missions into category 4 storms, they bias the box plot and cause it to be a lot more spread out. That could be the reasoning. Not exactly sure, though, what is causing that large spread. But once you move on from 0 to 34 knot wind interval and move on to the stronger wind fields or wind intervals, you start to see that spread really rapidly decrease. Again, especially once you start looking at, let's say, the wind speeds greater than 83 knots. Category 4, we return back to normal, what our expectation would be. With the 0 to 34 knot wind interval, we have our lowest percentage for that wind speed interval range is less than 5%. So we had a mission where less than 5% of observations were taken between 0 and 34 knots. And then we had a few missions where the percentage was as high as almost 30%. Now, interestingly, we don't actually have a case where the observations taken between 0 and 34 knots are where that was 0. So basically, for every single mission into a category 5 system, the observations taken between 0 and 34 knots were non-zero. And you'd expect that because with a category 5 cyclone, the winds in the center of the storm are going to be extremely weak because it's steady state, that eye is extremely clear. And so when the hurricane hunters intersect through that eye, they are guaranteed to reach winds that are less than 34 knots. So they're always going to observe, they're always going to have observations less than 34 knots. But again, looking at the rest of those wind speed intervals, you see the average or the spread around that average really rapidly decrease. Now moving on to our GFPIs, that GFPI analysis, we wanted to basically answer the question of, as you investigate stronger and stronger storms, how does your count of successful GFPIs change? And what we found was there was an inverse relationship. So if you're investigating a stronger system, you expect to intersect the gale force threshold fewer times. Now, this relationship is very weak. It's weak for both the adjusted data set and the original data set that includes observations taken at pressure levels less than 650 hectopascals. So with that in mind, this doesn't really provide any actual information, but it does confirm our suspicion that as you stronger systems that usually are bigger, there's a big caveat with that, but when you are investigating systems that are usually bigger, you're going to cross that gale force wind threshold fewer times. Now, something that did provide some useful information was analyzing the chronological success of the GFPIs. When you enter the storm, 79% of the time, you're guaranteed to cross over that gale force wind threshold. But as you start making those triangles, those alpha triangles that I was showing you guys earlier, that success rate does drop off down to 77% after alpha triangle 1, or after your intersection creating alpha triangle 1. Once you're creating alpha triangle 2, 74% of the time, you're going to cross the gale force wind threshold. Alpha triangle 3, 75% of the time, that's probably just noise, but in general, you're seeing a decreasing trend. In alpha triangle 4, you're intersecting that gale force wind threshold 61%. Now, once you move on to alpha triangles 5, 6, and 7, we have so few instances of that playing out because usually reconnaissance missions don't fly that long into cyclones. So they're not going to have the amount of time to create those triangles, that many intersections. So with those, there's no statistical significance, so we'll just disregard them. But moving on to your exit leg, every mission has an exit leg because they're all exiting the storm. 64% of the time, the hurricane hunters successfully cross over that 34-knot wind radius. That actually is a significant drop compared to the 87% success rate when you include observations taken at pressure levels less than 650 hectopascals. And what this implies is that for stronger, or for your reconnaissance missions, as they exit the storm, they often gain altitude before crossing over that 34-knot wind radius. Now, here's our key findings, a summary of our key findings. Again, we observed patterns and distributions across wind speed intervals for 6 tropical cyclone categories. Excluding tropical storms, the maximum frequency in each hurricane category peaked at that 34 to 50 interval range. We also found that there's that statistically significant inverse relationship between the number of successful GFPIs and the mission Vmax. And again, noting that basically for missions into stronger hurricanes, you expect fewer successful GFPIs. And then we evaluated the chronological success rates of the GFPIs and found that the GFPIs into the earlier parts of the mission are the most successful. And we found that the aircraft usually gain altitude, or about 37 to 40% of the time, that aircraft usually gain altitude prior to a successful GFPI on the exit leg when they're exiting the storm. So future studies, before performing a future study with this data set, I do recommend a more robust outlier identification method, as of course I had to do this process manually, and I'm human, so that leaves room for error. And then also I would incorporate the NHC best track database. Basically, that database includes a lot of information for tropical cyclones. One such is your radius, your wind radii for the 34-knot wind radius, 50-knot wind radius, etc. And so one interesting thing you could analyze is how basically for a plane, whenever it's making that GFPI, when it's turning around to go, let's say, back into the storm, if it does not successfully cross your gale force wind threshold, what's the distance that they were from the theoretical 34-knot wind radius before they turned around? That could provide some useful information for hunters on, oh, maybe we can just extend our flight by a few miles and we can cross that threshold at a lot higher success rates. We could also evaluate the relationship between successful GFPIs and integrated kinetic energy instead of Vmax. Of course, Vmax, while you have stronger cyclones that are usually larger, you have many instances where you have a strong cyclone that's super small. For instance, you have like Hurricane Charlie that fit within Hurricane Ian's eye. So you have quite a large variance. And integrated kinetic energy, IKE, takes into account the size of the wind field. So theoretically, you should expect with higher IKE values to have fewer successful GFPIs. And that's something you could use the NHC best track database to investigate. We'd also, instead of using Vmax, we could use IKE to separate your emissions and then calculate the interval frequency averages by IKE. But this study really sets the foundation up for using the GFPI dataset to explore how the reconnaissance mission patterns and tendencies optimize tropical cyclone 34-knot wind structure forecasts. I was not able to get to that in my project, but that's something that this project does set up the foundation for. Now, with that in mind, I would like to move on to my acknowledgements. Thank you, Dr. Alquist, for dedicating so much of your time, for meeting with me weekly and answering my questions and being such a great mentor. I'd also like to thank Dr. Michael Kozar and Dr. Heather Holbach for being my subject matter experts. Dr. Holbach was important for her SFMR expertise. And Mike, he's one of my colleagues at RMS H-Wind, and so he has been a huge mentor for me as well.
For the people in the audience, they might want to know that those two people are married.
Yes, they are also married. I also like to thank Dr. Ingo and Dr. Misra. They are not married, but I'd like to thank them for guiding me through the research process as well. I'd like to thank Florida State University for the honors in the major program. And I'd like to thank NOAA, NHC, and the Air Force for collecting the data and making it publicly accessible. Now, with that in mind, here's my references and any questions.
I want to start, and then there'll be some public questions, and then after that, let everybody get stretched back with your drink of water, and we'll come back for the oral exam after that. But there's some open questions first. First one I want to ask has to do with, you said you work at H-Wind, which is owned by Moody's. Now, what's Moody's involved with? Why would they be interested in hurricane?
Right, so they deal a lot with insurance, and insurance, of course, here in Florida, there's many assets that have to be insured. Of course, your home has to be insured, businesses do, and so what they're interested in is providing data to insurance companies on basically cost of damages, those estimate damages, and so then those cost estimates are sent to the insurance companies, who then use that data to basically figure out how they're going to.
Now, does Moody's, do you know what reinsurance is?
Yes.
Does Moody's sell reinsurance?
I'm not familiar actually with that. I'm pretty sure they do direct insurance stuff, but they might do some reinsurance.
Do you know what the reinsurance industry is?
Yes, reinsurance industry is insurance for insurance companies.
So how does that work with hurricanes? Because this is a big money thing. And this is why they're willing to do this kind of stuff.
Well, so an insurance company, of course, holds a lot of money and assets, but whenever you have a really busy and active hurricane season, you can have huge costs to the insurance companies. And so they might have to purchase their own insurance policy based off the season, and they purchase that from reinsurance companies.
So my understanding is that if an insurance company contacts a reinsurance company, what they work out is a contract that says that the insurance company will pay for all the losses up to so many $1 billion. And if the losses exceed that many $1 billion, then the reinsurance company will pay the losses up to a certain cap. And so if the year isn't that bad, the insurance company buys the reinsurance and they never have to use it. But if they have to use it, it can be extremely expensive for the reinsurance company to pay out this money. And so when they're interested in things like how big is the tropical storm force, you're looking at areas of how big can the damage be. And so this is helping them get an idea of how large a risk they face. when they do this, so that they can, because both sides are trying to make money. On this, the reinsurance company doesn't want to pay more than they have to for this. But, that's right, the insurance company doesn't want to pay more than they have to, but the reinsurance company knows they gotta charge a lot, because if they actually have to pay, they're gonna have to pay it up. It's gonna be very expensive. So that's why they do this. A hurricane, my understanding was that Hurricane Andrew in the early 1990s exposed how fragile the hurricane industry was to major hurricanes. Normal insurance industry, it has like car accidents, slip and falls, dog bites. These are happening every day, and they can have very good statistics. But when you start talking about these hurricane things, it's like most years, the insurance, the people who own their homes never file anything with respect to hurricane claims. And then there'll be a year where a major hurricane hits and everybody in the city files a claim. Whereas in a normal year, for example, car accidents, some small fraction which they can help it. And so insurance companies just went broke with Hurricane Andrew. And so they had to re-examine how they can do this. And so it involved rethinking the insurance industry, as well as getting a whole lot more statistics. Okay.
It's maybe because I came in late. Can you remind me what GFPI is?
I
Yes.
was going to ask you to do that.
Of course.
I realized once you got going that you said it once at the beginning and then.
Yeah, so the GFPI is the gale force potential intersection. It's a possible time, a moment where they intersect that 34-knot wind radius. Does not mean that they necessarily do, but it's basically where they could cross over that 34-knot wind radius. And in this case, they had 4 successful GFPIs where they crossed through that 34-knot wind radius at the beginning and at the end when they're entering and exiting, and then 2 times when they're making that alpha triangle pattern.
So it's a likelihood of a time?
It's a likelihood, yeah. So it's basically documenting an instance where they could have crossed over because they're, let's say, approaching that 34-knot wind radius, because there are parts of the storm where they're approaching the eye of the storm, and there's parts of the storm where they're exiting the eye, and so they're approaching, let's say, the 34-knot wind radius.
Okay. And you also explained to me that some of the other factors involved is they may not turn on this microwave sensor. Once they turn it on, they might find out they're already inside they're already exceeded the 34 knots, and so they missed.
Yeah.
There, or they might not be at the right level
Altitude, yeah.
where they're sensitive. Other questions with that?
So just looking at the wind vector there, that actually, I only now understood that this is from the surface microwave.
Right.
Where did they get the wind vectors? I would say the rough.
Okay, so yeah, the roughness values only get you your wind speed. They then use the flight level winds that they observe when they're flying at this pressure level, which they observe, of course, through onboard institute instruments. So they'll observe that wind speed.
Really wind measure that they have playing.
Exactly. Yeah. So then they use the magnitude that they detect at the surface and then the winds that they detect when they're flying. That's why they try to fly as low as possible.
Do you know if because for dynamical reasons with the way friction can change the pipe, wind speed can change the pipe. Do you know if they do any adjustment?
With the direction?
Or do they just take the flight level direction?
I do not know. I think they just translate it downward. I don't think they make any adjustments. But that's why, like, you can't use wind measurements taken by the Gale 4 or the G4 plane, which flies high in the atmosphere and is actually sampling the anticyclone above the hurricane.
One of the things that I like about being on these committees, not in your field, is you learn all kinds of cool things you have no idea about. On the previous instance of this, I was on a committee of a student who analyzed observations in thunderclouds and storm clouds. And there was a systematic bias that he had to adjust for because there were some clouds that the pilot would just not fly into.
Right.
So does that play a role here, or are these really more or less neutral? These flights go on a plan?
That's a good question. So normally they do not have to make many adjustments to their flight path. There are instances where, let's say you have a really convective rain band. I can actually let's see, at the very end of this. So right here, this is a pretty convective rain band. They might have to dodge, weave in and out of the rain band. But for the actual eye, where you have really strong winds, it's actually quite steady state. So if you ask a hurricane hunter, how was the flight? If it's into a Category 5 storm, they usually are like, hey, this is actually pretty nice. They don't like the tropical storms because those are usually very convective and turbulent. Yes. But for steady state systems, like a strong Category 5 system, yeah, those winds it's very steady state and the turbulence is not as bad. So they can fly pretty much in any part of the storm.
So did you, during your analysis, look at during a season at each of the storms, what the frequency of the winds were for each storm that time instead of just the category of the storms?
No, I did not. That's a good question because you could find that there's cases where maybe the cyclone, whenever they're analyzing cyclones earlier in the season, they prioritize trying to observe the structure more in those earlier parts of the season. But we do not know how that actually changes across the season. But it's a good question, something that could be get investigated further.
Okay. Sorry. So I guess if you had a take-home sentence for how your GFPI research in this case impacts, I suppose, your industry would be insurance, what would that be? In terms of what your research says for your future dealings and for the company that you work for?
I would say probably the major takeaway is that for those stronger storms, you're not going to have as many intersections. And so when we're talking about a really large cyclone, you're going to have to hope that there's other data out there. Hopefully now they're flying out, or now they're using those sail drones, which they usually don't try to fly into the middle of the storm. They try to fly, or they not fly, sail them in the exterior parts of the storm. So those can be useful for getting maybe one or two more 34 knot wind intersections. But it really emphasizes that we need to continue to keep maintaining the number of satellites that we have that are suitable. Because if we start to let that number decrease, we'll have issues with understanding how wide the wind is. And of course, that impacts our understanding of storm surge and that kind of stuff.
So,
Yes, no.
I'm trying to still understand this inverse relationship between Vmax and GFPI that you talk of. Because in my understanding, as Vmax increases, the storms become more compact and more symmetric.
They do definitely become more
So,
symmetric.
are you saying that the 34 knot wind boundary becomes wider in stronger storms, or would it also shrink and become stronger? Because I would expect
By angular momentum, yeah. That's a good question. I think Rmax definitely does shrink with stronger storms, and Rmax is the radius of maximum wind, and that does play a huge role in the angular momentum, where basically if you think of a figure skater, if you have a figure skater that spreads her or his arms, they're going to spin weaker or slower than if the arms are tucked in. But as far as the 34 knot winds, you might see a decreasing trend with some stronger storms. But when you think of, let's say, just on the scaling purpose, a tropical storm, the winds could be as small as like Rhode Island, or like super small, like a very small patch of winds. Or you can have, but with a 34 knot wind radius for a Category 5 system, like a Hurricane Ian, you could have the wind field extend from as far as like the Big Bend of Florida down to, you know, the Keys. So even then, even if it does compact slightly, it's still in general going to be much larger than your tropical storms and your category 1s. There might be a small difference though, whenever you start looking at like category 4 systems versus 5 systems, or, you know, 3 versus 5.
And the other thing is when, I don't know how these flight reconnaissance plans are made. But before they even fly, there's a flight plan that they work on, right?
Yes, they usually develop a flight plan.
So, it looks like this flight plan and the observations they make is deliberate, right?
Mhm.
That they are trying to observe as much of the strongest winds as possible.
Yes, their priority is to measure the strongest winds and to find where the center of circulation is.
But it looks like you're attaching more importance to the 34 knot wind.
I'm attaching importance to like them also prioritizing structure when they're creating these flight plans, because they really prioritize just finding the strongest wind speed, which is very important, and also finding the center of circulation, which is important for understanding its trajectory.
Which I believe is motivated by the success in forecasting, because assimilating these strong winds has a huge impact on how the storms are initialized.
Of course, right? Yes, yeah.
So,
You see a huge jump in the model accuracy whenever you start ingesting or putting into the model the Air Force reconnaissance data or the NOAA reconnaissance data. But you know, we can see even with the forecasts of intensity and track that they continue to have errors, and they're asymptotically approaching a limit of like improvements. So one of those barriers to continuing improving those intensity and trajectory forecasts is structure. If we don't understand the structure of the storm, then as well as or structure of storm, in addition to the other elements of the storm, then you start to really approach that asymptote. But if we can understand better how the structure of the storm evolves over time, then we can hopefully make steps towards improvement of both that forecast and also the forecast of the intensity and trajectory. Because of course, trajectory is impacted by how the environmental winds steer the storm and et cetera.
Okay, so I want to say something that it gets somewhat into your question about the findings, and what I want to do is to refer to. So Chandler has been doing this project through this H-Wind company where he's supervised by Dr. Michael Kozar, who's an outside committee member. Dr. Kozar could not be here. So Dr. Kozar works for H-Winds, which is related to this insurance industry. His wife, Heather Holbach, is a NOAA scientist. And she is at least, I think the NHC expert on this.
SFMR, yeah.
The SFMR, the microwave radiometer that's used for this. And she also flies on these reconnaissance missions. So she's got direct experience. She's looking at things really as a scientist when she does this. I think Michael Kozar is still looking from the perspective of a PhD scientist, but he does work for a company that has these broader economic issues. So this is what Dr. Kozar wrote in terms of answering your question. Said Chandler did a really nice job collecting, processing, and visualizing a large amount of data from National Hurricane Center. The aircraft data he worked with is in a rather archaic format, and he found out the files aren't even formatted consistently. So it takes a lot of effort to read in as much of the data as he did, especially as an undergraduate research project. This work was much appreciated, and the data set he built is probably the most significant part of his research, as it can be used as a foundation for plenty of future projects that he might want to work on. So a lot of it was building this.
Yeah, it was laying the foundation.
And for those of you who haven't, working with data is intense. In meteorology, I'll roughly say there are 3 broad categories that people work in. Data analysis, you have to learn to work with these, finding the bad data and the inconsistent formats and all this other stuff. There's the theoretical stuff, where it takes strong math skills and figuring out approaches, you know, what's a good model to use. And then there's modeling, computer modeling that takes computer skills. And
It's kind of the in-between of the two.
each one of them requires some special skills, and you don't find many people who are good at more than one of those areas because of just the expertise that it takes to be good enough in any one of those. So I think it's really good that he's gotten his hands dirty with learning how to get exposed to. So, yeah. Last question I've got, but unless other people have, some things are, okay, so you're also a statistics major. Now, we talked about identifying outliers, and one of the things you said was you used a mean absolute deviation. We can go back to that, rather than the standard deviation. So what is the advantage of using a mean absolute deviation from what's probably more common of the standard deviation?
You know, I basically was trial and error. I used both and found that the sensitivity for the standard deviation was just a little too much. And of course, if we look at, let's say, like one of these curves, you have many instances, actually, this is probably not a great one, but you have many instances where the points deviate slightly from the rest of the data, but are probably just noise and probably are still accurate.
I can give you, there is a very good reason why, and that the outliers, when you look at a standard deviation, you're squaring the difference between a value and the mean.
Yeah.
If you have an outlier, a few outliers can make an enormous contribution.
Yeah, to your standard deviation. Yeah, that's true as well.
Enormous contribution. And when you're just dealing with the absolutes, those outliers don't skew the value so much.
Right.
And so it's easier to find the outliers.
Yeah.
When you do that. I mean, you could also, another way of doing a similar kind of thing would be to sort the values into percentiles and to say, how often does it lie outside a certain percentile? Because that, like you said, with the median, it's not affected by the really extreme.
Yeah, that's a good
values.
point. Yeah.
And then by dealing with that, you can see these tails, but outliers can really distort standard deviation values.
Yeah.
Okay, do we have any other questions? So what I propose we do is thank Chandler for his presentation.
Yep.
Get a drink of water, stretch, use the bathroom, whatever, and then we come back here for the oral exam.
All right. Thank you for everyone that came to attend virtually. I'm going to go ahead and end the session now.